Hey everyone, and welcome to section 2.5 about the intersections of lines and planes in R3. And indeed, the goal of this section is to determine either the point of intersection, if we're given two lines or a line and a plane, or to determine the line of intersection if we're talking about two planes. And as is often the case, there's more than one way of doing this, typically. And so what I'm going to do in the upcoming videos is present a method or a couple possible methods that will work. So in this video, we are going to do 2.5.1, the point of intersection of two lines, and we're going to do that by looking at example 2.5.1. So right here we have a lovely method outlined for finding the intersection. I'm going to do the example and show you the method sort of step by step rather than reading through the method first. So let's look at the example 2.5.1. It says to use vector methods to show that the lines intersect at a point. That is review. Actually, that is something that we did in our relative positions unit. So that will be a little reinforcement of material that we've seen before. And then we are asked to find their point of intersection, which will be using the method that's outlined in this box above. So let's start here by doing the first part, which is entirely something that we've seen before, and then we'll proceed to look at the method that's outlined above. So use vector methods to show that the lines intersect at a point. So we had a decision tree, a flowchart to go through with this, and the first thing we need to do is identify the points and the direction vectors that we can see on the two lines. So there is point 1, 7 minus 3 minus 2 on line 1, and the direction vector is the vector 2 minus 1 minus 1. L2 is in symmetric form, so let's put it in parametric form to be able to read things more easily. Y is 6 plus t, and z is minus 1 minus t. So we can say point P2 on line 2 is 1, 6 minus 1, and we can see direction vector D2 as 1, 1 minus 1. So the first thing that we had to do to distinguish between the positions, or to determine the positions, relative positions of the lines, is ask ourselves if the direction vectors are parallel. Are they multiples of each other? Is D2 equal to k times D1? And you can kind of look at it and see that it isn't, but let's be a little bit more formal here. We'll set up a little system of equations based on the components. 1, the x component of D2 would have to be 2 times k. 1 would also need to be minus k. Well, that immediately doesn't work. And minus 1 would have to be minus k. Right? So in the first equation, we would have k is 1/2. In the second equation, we have k is minus 1. That is inconsistent. And if it is inconsistent, then the vectors are not parallel. And if the vectors are not parallel, then the lines are intersecting or they're skew. Now, that's good because we wanted to show that they were intersecting, so we're on the right path. To show that they are intersecting versus skew, we have to show that lines are coplanar. Right? When they're skew, they are non-coplanar. When they are intersecting, they are coplanar. And so to do that, we needed to examine the triple scalar product, P1, P2, dotted with D1 cross D2. So let's calculate our P1, P2. So P1, P2, we're going to take the coordinates of P2 and subtract the coordinates of P1. So 1 minus 7 minus 6. 6 minus minus 3, so 6 plus 3 is 9. Minus 1 plus 2 is 1. Right, so there's P1, P2, the cross product, so D1 crossed with d2, well, let's get those vectors written down. And 1, 1, minus 1, 1, 1. So 1 minus minus 1 plus 1 is 2. Minus 1 minus minus again plus, so 1 and 2 minus minus 2 plus 1 is 3. So then the triple scalar product, P1, P2 dotted with D1 cross D2 is, right, so you remember that we are just going to multiply the components and add them up. So we have minus 12 plus 9 plus 3, which gives us 0. So the vectors are coplanar. If the vectors are coplanar, the lines are coplanar, and that means that they are intersecting. So our lines do indeed intersect at a point. And that is the first thing that we were asked to show. So we have done the first part of example 2.5.1, the review, the procedure that we had seen before, and now we're going to go on to the second point. We're going to find the point of intersection, which means that we are going to apply the method that's outlined on your page or screen. And so this says to find the point of intersection of two lines, we may use the following procedure. So let's go through this step by step. Part 1, write both lines in parametric equation form using different parameters, either t1 and t2, s and or t and something like that, and set corresponding equations equal. So let's go and do that. Well, the first part here, we've done line 2. Let's put line 1 in parametric form, which is going to tell me that x is 7 plus 2 times, and it says t, but I'm going to switch. It tells me to use different parameters. I've used t for line 2, so I'm going to use s. 7 plus 2s. Y is minus 3 minus s, and z is minus 2 minus s. So I've written both of them in parametric equation form, and now we're supposed to set the corresponding equations equal. So the x, the y, and the z. In other words, 7 plus 2s is equal to 1 plus t, minus 3 minus s is equal to 6 plus t, and minus 2 minus s is equal to minus 1 minus t. So there is a system of equations, and we have done the first part of the method. Now the second says pick 2 of the equations and solve them using high school methods. So I'm going to take, it doesn't matter which 2 I pick, so I'm going to take the second 2, and I'm going to solve them as I would solve a system of equations in high school. So I'm going to bring all of the constants to one side, all of the variables to the other. So the first equation becomes s plus t is equal to minus 9, and then I will get s minus t is equal to minus 1. So there's my system. Now I am going to take advantage of something that is sitting in front of me. The coefficients of t are opposite sign, and I can just add those equations together. So I'm going to get 2s, the t's will cancel out, is minus 10, and so s is minus 5. And if I go and plug it back into either one of the equations above, I will see fairly easily that t has to be minus 4. So there, we're done the second step of the procedure. Now the third step says test, right? Because there was an extra equation here. And so we need to make sure that our values actually do satisfy that equation. Now, strictly speaking, we've already shown that the lines are intersecting, and so unless we've made a computation mistake, this has to work. That's not necessarily the case. If we hadn't if you just started with two lines that you didn't know the relationship for, that might actually not work in the last equation. So we are going to test, we're going to be required to test every time because you're given three equations. You should really test that all three of them work. But there is an argument to be made that we know it is going to work in the last equation because of the first part of the example that we did, right? Because we did this procedure to show that the lines, in fact, are intersecting. So let's just go and do the final test to make sure our computation was correct. So our left-hand side of that first equation is 7 plus 2s, which is going to be 7 plus 2 times minus 5, so that's plus minus 10, which is minus 3. The right-hand side of that equation is 1 plus t. T is minus 4, so 1 plus minus 4, which is, again, minus 3. So those two are equal, and so we have indeed shown that our solution matches all three equations, and we can pass on to the fourth step. We weren't asked to solve for s and t. We were asked to find the point of intersection of the lines, which means that we have to take one of these, we have to plug the solution into either line to find the point of intersection. So it really doesn't matter which one we do, they will give us the same. So I'm going to go into line 2. So L2 tells me that the x is 1 plus t, which is 1 minus 4 is minus 3, and y is 6 plus t, which is 6 minus 4, which is 2, and z is minus 1 minus t, which is 1 plus 4, with minus 1 plus 4, which is 3. And so that tells us that our point of intersection is the point minus 3, 2, 3. So minus 3, 2, 3 is the point of intersection of our two lines, of the point of intersection of L1 and L2.